What if the device designed to save your life was engineered with a fatal flaw? A chemical time bomb ticking away just inches from your face. What if this last line of defense, this marvel of engineering, shared its core ingredient with the very same material used in industrial explosives?
And weapons of terror. This isn't a hypothetical. It's the true story of a molecule that became a weapon, an innovation that became a liability, and a corporate secret that triggered the largest, most complex automotive recall in human history. This is a chemical investigation. Our story begins not with a car, but with a molecule.
A simple, elegant structure of nitrogen, hydrogen, and oxygen. Ammonium nitrate. To an engineer in the 1990s, it was a miracle compound. The holy grail of airbag propellants. It's incredibly cheap to produce. It's compact. And when triggered, it produces a massive volume of harmless nitrogen gas almost instantly. It is the perfect engine for an airbag. A tiny, solid-state rocket motor designed to inflate a life-saving cushion in less time than it takes to blink.
But to a chemist, ammonium nitrate is a paradox, a beast that demands to be tamed. Its incredible power is also its greatest liability.
This is the same chemical that, when mixed with fuel oil, was used in the 1995 Oklahoma City bombing. A compound capable of both saving a life and leveling a building.
The story of the Takata airbag crisis is the story of this fundamental conflict. The engineer's desire for a cheap and powerful gas generator versus the unyielding, dangerous chemistry of the molecule they chose to harness.
To understand how a life-saving device becomes a grenade, we have to look deeper into the very structure of the material itself. Inside every inflator were small, disc-shaped wafers of propellant, looking like harmless aspirin tablets. The core ingredient was ammonium nitrate. Now, most manufacturers knew this chemical was volatile. They had experimented with it for years. They controlled it by mixing in other chemicals called stabilizers,
which act like a chemical cage, holding the ammonium nitrate in a stable, predictable form. But the Japanese auto parts giant Takata made a different choice.
A bolder, cheaper choice. The fatal flaw, the deliberate, cost-cutting decision that sealed the fate of millions, was Takata's removal of those phase-stabilizing additives.
They believed they could contain the chemical's inherent instability with brute force alone, the strength of the steel inflator housing.
They were betting on physics to conquer chemistry. It was a gamble worth billions, and it was a catastrophic miscalculation.
Because ammonium nitrate is a chemical shapeshifter. As the temperature inside a car swings from a cold morning to a blistering hot afternoon, the molecules inside those propellant wafers begin a destructive dance. The solid crystal structure of the ammonium nitrate literally breaks apart and reforms. Imagine a solid brick that, with every daily temperature cycle, crumbles slightly, its internal structure weakening, becoming more porous and fragile.
Year after year, summer after summer, the solid propellant inside millions of airbag inflators was slowly, silently, turning to powder. This physical breakdown was the first step toward disaster. It dramatically increased the surface area of the propellant, turning a material designed for a controlled, rapid burn into something far more volatile.
But temperature was only one enemy. A more relentless one was lurking in the air itself.
Meet the deadly trinity: heat, humidity, and time. These three forces waged a constant, invisible war against the integrity of the propellant.
The most dangerous of them was humidity. Ammonium nitrate is intensely hygroscopic, a scientific term meaning it aggressively absorbs water from the air.
Moisture, microscopic droplets, would seep past the inflator's seals, drawn into the propellant wafers like a sponge.
This moisture didn't just dampen the material, it acted as a catalyst, actively accelerating its decomposition, breaking down the chemical bonds,
and making the already fragile wafers catastrophically unstable.
This is why the first signs of the crisis didn't appear randomly. They emerged in specific, predictable locations.
In 2004, the driver of a Honda Accord in Alabama was killed by shrapnel from an airbag in a minor accident.
The case was mystifying. Then more reports trickled in. Cars in hot, humid climates like Florida, Texas, Puerto Rico,
and Malaysia began to fail at an alarming rate. The combination of intense heat cycles and moisture-saturated air was the perfect recipe for disaster.
On a map, the recall hotspots were a clear indictment of the design. The inflator wasn't failing because of a single defect.
It was failing because it was fundamentally incompatible with the world it lived in. The device was losing its unwinnable war against the laws of chemistry and entropy.
Every passing day, every humid afternoon, brought millions of vehicles one step closer to a critical failure.
This brings us to the moment of impact. The crucial milliseconds that determine whether an airbag saves a life or takes one.
A properly functioning inflator is a controlled, rapid burn, a process called deflagration. The propellant burns from the outside in, at a speed of around 200 miles per hour, producing a massive volume of gas that inflates the airbag.
It is a powerful, directed push, a firm, fast cushion.
But after years of being ravaged by heat and humidity, the propellant inside a faulty Takata inflator was no longer a solid, stable wafer. It was a degraded, porous powder with a vastly increased surface area. When the crash sensor triggers this compromised propellant, the result isn't a controlled burn. It's a detonation.
The burn rate doesn't just increase, it explodes from an inflation speed of 200 miles per hour to a detonation velocity of over 6,000 miles per hour. It's the difference between a high-speed gust of wind and a bomb blast. This near-instantaneous release of energy creates a brutal shockwave,
A pressure front that the steel inflator housing was never, ever designed to withstand. The metal canister, intended to safely direct the flow of gas, instead ruptures.
It shatters, turning into a spray of razor-sharp shrapnel that fires directly into the vehicle's cabin, through the very airbag that was meant to be a protective cushion. The safety device had transformed into an improvised explosive device, aimed directly at the driver and passenger.
So, was this crisis inevitable? Once the decision was made to use unstabilized ammonium nitrate, the outcome was all but certain.
But what makes this a true catastrophe is the human element. Evidence later revealed that Takata engineers had known about the dangers for years.
Internal tests showed catastrophic failures, ruptured inflators, and inconsistent results.
Instead of raising the alarm, the company allegedly concealed the truth, falsifying test data to present a picture of safety and reliability. To its automotive clients, it was a secret kept for a decade, while the chemical time bombs were installed.
In over 100 million vehicles worldwide.
This wasn't just a corporate scandal or a manufacturing defect. It was a failure to respect the fundamental laws of nature.
Compounded by a culture of secrecy. It stands as a chilling reminder that in engineering, the most elegant solution is not always the cheapest.
And that ignoring the inherent properties of a material, no matter how well contained you believe it to be,
is a gamble against odds that will eventually win. The story of this molecule is a cautionary tale written in shattered steel.
And human tragedy, a lesson about the invisible forces that govern our technology, and the catastrophic price of underestimating them. If this investigation gave you a new level of understanding, subscribe for our next deep dive.